Hello, am I audible?
Yes, ma'am.
Yes, ma'am.
Okay. So today's topic is application of derivatives. So we'll wait for a couple of more minutes. And we'll start at 8:05. Okay. Just wait for 3 minutes. Okay, so let's start. So these are the topics we will see in this lecture. So we'll start with the very basic thing, which is local maxima and minimum. My voice is clear, right? Hello?
Yes,
Okay. Yeah. So we first talk about local maxima and minimum. So what are these two quantities? So first thing is, as we always see that we can associate two quantities with each other via function. Function is what? So function is nothing but a rule from one set to another set, which possess two quantity or two qualities. That for every element, we should have a unique output, right? Or for every input, we should have a unique output. So this is a function, and for any function, we can define its property, which is known to be the differentiability of function at particular point. And now we will see how this derivative of a function or differentiability of a function will help us to know or to gain much more information about a function, right? So first property is local maxima or minimum. So suppose if we have a function and the graph of that function is denoted by this particular curve, Then here, over some points, you see that suppose at this point, this point x is equals to, let's say, -2. Then at this point, what is happening? If you consider a very small neighborhood here, the small neighborhood means very small interval over this -2. And what are the values of, what are the functional values attaining over this particular small interval? Then here you observe the property that every value of a function uh, is actually smaller than the value of function at x is equals to -2. That means in this neighborhood, the f of x is less than equal to f of -2 for all x belongs to whatever small neighborhood you consider here. So suppose I'll consider -2.5 and uh, let's say 1.5, -1.5. Right? I'm considering very small neighborhood of 0.5. So in this particular neighborhood, what is happening? Function is gaining its maximum value at x is equals to -2. Right? That means f of x is less than equal to f of -2 for all x belongs to -2.5, comma -1.5. Right? So such kind of nature is, very significant to observe that at which point our function is gaining maximum value or minimum value. So those things we can evaluate using with the help of derivatives. Okay. So first, let's define what are the local maxima and minima. So what is local maxima? Okay. So local maxima is nothing but the but that point of your domain. So local maxima. So we say x is equals to x naught is a point of local maxima if there exists a small delta, and this is sign for there exist. I hope you guys remember. Okay. So if there exists delta greater than 0, here we are just referring delta as very small number so that we can minimize our interval over some small distance. For example, if I have this kind of thing, then here I can take very small neighborhood to say that this point is my local minimum. Okay. Here in case in this picture, it's nothing but local minima, so all greater than equal. Sorry. So what is a local maxima? So local maxima is nothing but that point where our function is uh, achieving the maximum value over some very small interval. Right. For that small interval, we are referring delta greater than 0. Okay. So if there exists a delta greater than 0 in such a way that f of x is less than equal to f of x naught, this is less than or equal to f of x naught for all x belongs to open interval x naught minus delta, comma x naught plus delta. And this thing you also can write in the session that for all x which lies between these two quantities, that x naught minus delta is less than. Okay, so x naught minus delta is less than or equal to x is less than equal to x naught plus delta. Okay, so this is a definition of local maximum. And similarly, we can define local minima also. So what is our local minima? So local minima is nothing. We say that x is equals to x naught is a point of local minima if there exists delta greater than 0 in such a way that f of x is greater than equal to f of x naught for all x belongs to again the small interval x naught minus delta comma x naught plus delta. And this thing you also can refer as that all x which lies between these two quantities x naught minus delta and x naught plus delta. X naught minus delta less than equal to x less than equal to x naught plus delta. So these are the definition for local maxima and local minima. Local maxima, local minima. Now we'll do. Now we go to the concept that how we can judge that a function has a local maxima or local minima at certain points using the derivative of function.
Can I take one example of global maxima and minima?
Yeah. Over this graph also you can find. So suppose at this point, or let's take very simple example. I'll take a parabola. Okay. So suppose you have this kind of parabola. So now here, suppose this is the vertex of parabola. Uh, let's take it here somewhere. X is equals to minus. Now, what can you say about this point? Is this a local maxima or local minima? X is equals to minus 1.
Minima.
minima, correct? Because if you consider a small neighborhood here, then all the values of function are actually greater than equal to this particular value. So this is one kind of example of local maxima or local minima. Okay, why we are saying this to be a local property? Because here we want just a small neighborhood. We don't want a function to be a function to attain its maximum value over the whole interval. Over the whole interval means, suppose I have a graph of a polynomial. Suppose this is some graph of a polynomial. Suppose this is a polynomial f. Then and it's increasing over here. That means over this direction, it's actually going to plus infinity, and over this direction also, it's actually going to plus infinity. Suppose it's increasing from these two directions. Okay. So in this scenario, what is happening? This function actually not gaining any maximum value, because its value increases as we approaches toward infinity here, and also goes toward minus infinity here. But what happening here, that there are certain points where the function is actually attaining maximum value, but over some small interval. So suppose this is another point x, so x naught. Then here it is a point of local maximum, because if you consider a small neighborhood here, then all those values the function is attaining over the small neighborhood is actually less than equal to the value of f of x. So certain points are local, right? It's not the global thing. Global means we don't need the maximum value over the whole domain. We want maximum value attained over a small neighborhood. The neighborhood can be very small. Whatever delta you want to choose, you can choose. Is that fine?
Yes, fine.
Okay. Now let's see how we can judge the this point of local maxima and minima using the derivative. Okay. So there is a theorem. So what does this theorem says? So it says that if a function has a local maxima or a minima at x is equals to x naught, and it is differentiable, at x is equals to x naught, then the derivative at that point is nothing but 0. Then f dash at x naught is equals to 0. Okay, so this is a theorem. So it says that if you have any local maxima or minima point, if function has any local maxima or minima, then and the function should be differentiable at that point, because if it is not differentiable, then we cannot say f dash at x naught is equals to 0, right? So if the function is differentiable, the function is also differentiable at that point, then the derivative at that point is nothing but 0. Okay, so this is a one thing. So we can use this thing to judge what are those points where a function can attain its local maxima or minima property. Okay, but here one condition we require, that is the differentiability at that particular point. Okay, so let's see the proof of this particular theorem. So we will see two proofs of this theorem. One is geometrical proof and other is a little bit descriptive. Okay, so geometrically what you can think, that suppose we have a local maxima or minima at that point. So suppose this is our function, and at x is equals to x naught, we are having local maxima. Okay, suppose this is a condition for local maxima. And since our function is differentiable, it will be continuous over a small interval, correct? So our function something will look like this, right? This curve type of thing will happen if we have a local maximum. And over here, if you draw a tangent, then what is happening? Our tangent is nothing but parallel to the x-axis, right? This is your x-axis. So here in this graph, what is happening at a point x is equals to x naught, our tangent is parallel to x-axis, and we know that when tangent are parallel to x-axis, derivative becomes 0. So this will imply f dash at x naught is equals to 0. And same goes for local minima also. So suppose this is some point x is equals to x1, and here the local minima situation is happening, right? And if you draw a tangent here, then also you find that this tangent is nothing but parallel to x-axis, and we know that if tangent So the tangent is nothing but parallel to x-axis. Please give me 5 minutes.
Ma'am, your voice is lagging.
Hello, am I audible? Hello? Can anyone respond? Hello? Am I audible?
Yes, ma'am.
Yes,
Yeah, sorry for that. Let's continue. So here we see that if we have a situation where the local maxima or local minima point occur, then what happen? Our tangent is actually parallel to x-axis, and when the tangents are parallel to x-axis, we know that derivative at that particular point is nothing but 0. So this is one geometrical proof you can say for this particular theorem, which says that if we have a local maxima or minima at certain point, then derivative at that particular point is nothing but 0. And here with one condition that our function should be differentiable at that point. Okay. And why we want this to be differentiable at that point? Let's try to understand that by example. So suppose I have one function which is actually not differentiable at that point, but that particular point is local maxima or minimum. So suppose I have a function which look like something like this. Okay. And here we have a hollow point. Right. So suppose our function is looking like this, and at x is equals to x naught, you can easily see that every value around this particular neighborhood, the function's value is actually less than equal to f of x naught, right? So here what is happening, that f of x is less than equal to f of x. So that means this point is point of local maxima, but here since the function is it is not differentiable at this particular point. Why it is not differentiable? Can anyone say? Where the function is not differentiable at this point, x naught comma f of x naught. Using the tangent, we observe that some graphs over tangents. Anyone, why the function is not differentiable at point x naught comma f of x naught? Because we can draw several
simple
tangents
zero.
there. Sorry, what? Yeah, so at this point, what is happening? We can draw several tangents here, right? And we know that whenever such point occurs, the function is not differentiable, right? And and also it is not continuous here. So you can use the continuity also, because here if you compute left hand limit, right hand limit, those are same, but it is not equal to the value of function. So one reason is the continuity. So it is not continuous. So since f is not continuous at point x naught comma f of x naught, so obviously it is not differentiable. So using that theorem, we cannot conclude that this is a point of maxima or minima. But by observing the graph, we can say, yes, this is a point of maxima and minima. Okay, so that's why this certain condition that it should be differentiable is required. Okay. Now let's see another proof of this particular theorem. So again, I'll write the theorem. So what does the theorem says? That if f has local maxima or minima at x is equals to x naught, and f is differentiable at x is equals to x naught, then this will implies f dash at x naught is equals to 0. So one proof we saw using the geometry of that particular function. Now will we observe the left-hand derivative and right-hand derivative behavior at particular point x is equals to x, because we know that it is differentiable. So left-hand derivative should be equal to right-hand derivative. Okay. So now let's say what is the left-hand derivative at x is equals to x, right? So it is given by this quantity, right? So left-hand derivative at x is equals to x naught is nothing but limit x going to 0 f of x naught minus f of x naught minus h by h, right? So this is the expression for left-hand derivative, right? Now here what we use, so we take first case. So case first will be, so let we have local maximum. So let x is equals to x naught is a point of local maximum. Now here I am referring a point of local maxima because for a function there could be several point of local maxima. It's not the case that it will always a unique point of local maxima. We can have several point of local maximas. Okay. So suppose here we are taking a particular case where I am assuming that the point is a point of local maxima, right? So if it is a point of local maxima, then what happens? Then for all x belongs to the small neighborhood, so that means for all x which lies between a small interval of this x naught, that means x naught minus delta is less than equal to x less than equal to x naught plus delta, we have this condition that f of x is actually less than or equal to f of x, right? Now here what is happening, this quantity, this x naught minus h can be in this particular interval, and we can simply imply that x naught minus h is actually less than or equal to we can take a small, very small h in such a way that this particular x naught minus h can lies between these two things, that x naught minus delta and x naught plus delta. So what does it imply? So it implies that f of x naught minus h is actually less than equal to f of x naught. And this implies that this particular ratio is nothing but greater than equal to 0. So what does it say? So it says that f of x naught minus f of x naught minus h is actually greater than equal to 0, which implies our left-hand derivative is greater than equal to 0. Okay, so we conclude that left-hand derivative is greater than equal to 0 if we have a point of local maxima at x is equals to x. Is there any doubt over this particular thing, over these
No, ma'am.
equations? No.
No.
Okay.
Ma'am,
Now let's
can you
go.
extend the date of week 7 graded assignment?
Sorry, what?
Extend date of
No,
week
no,
7
actually
graded
dates,
assignment.
no, dates can't be extended.
Ma'am,
And also that's not in my hand. So
okay.
yeah, so if you want to request, you can request to sir, but see, I don't think it's possible to extend the date because they give us a very strict instruction over the graded assignment deadlines. They won't extend. It's an 80% chance that they won't extend, but you can request to sir if he can do something. Okay.
Because ma'am, week 6 graded assignment deadline is I think 13, and week
Okay.
7 is 15.
Oh, they only 2 days.
Yes, ma'am.
Okay. So I think this happened because of quiz and all. But see, you can talk to sir about this because I actually can't do anything. Again, once I will tell him, I'll have a talk with him that can we do or not. And I'll let you know in the next session. Okay.
Okay, ma'am.
I'll talk with sir. Let's see what he says.
Okay.
But try to complete it before, on 15th, because I don't think they
ma'am.
will extend. Okay.
Yes.
Now, let's try to see what will be the right-hand derivative here. Okay, so what is right-hand derivative at x is equals to x? Okay, so right-hand derivative is given by this particular limit, that limit h going to 0, f of x naught plus h minus f of x naught upon h. Now, again, at x is equals to x naught, at x is equals to x naught, we are having local maxima, right? Local maxima. So it means that f of x naught plus h will be less than or equal to f of x naught. And this will imply, because of the maxima thing, right? At x is equals to x naught. Again, you can use these steps to conclude this particular inequality, but it's quite clear that we are having local maxima, so f of x naught will be the largest value, right? So largest value means it will be greater than or equal to any quantity. So that any quantity is here f of x naught plus h. So it simply implies that f of x naught minus h, f of x naught plus h minus f of x naught is actually less than or equal to 0, because I am taking this term over left hand side, right? So what does it say? So it says that our right hand derivative is less than or equal to 0. But since it's given to us that f is differentiable, differentiable at x is equals to x naught, what does it mean? So it means that left hand derivative should be equal to right hand derivative. Right, but left hand derivative is less than or equal to 0. Left hand derivative is greater than or equal to 0, and right hand derivative is less than or equal to 0. So it simply implies that left hand derivative equal to right hand derivative is equals to 0. Right. So ultimately, what we get that f dash at x naught is equals to 0. Okay. So this is one algebraic proof you can see for the particular theorem. Is there any doubt in this proof or in this theorem? Because it's very important theorem. We can see. Okay. Now let's move to the next topic. Or we can do one simple example of this particular one, local maxima, local minimum. Okay, so you guys can find. So let's try to solve this question. So question is, find the points of local maxima and minima of the function. It's a very simple question number. F of x is equals to x to the power, or you can say 2x to the power 4 minus 27x plus 10. Okay. So I'll give you 2 minutes. You guys can quickly calculate and answer in the chat box. Okay. Just 2 minutes. It's not that difficult. You just have to calculate the derivative and solve the equation. You will get the answer. And also tell me which are the points of local maxima or minimum. And then if you calculate 1 point, then find out it's a maxima or minimum. Are you guys solving this question?
We are getting x as root cube of 9 by 2. So we have to put, right?
Right. Let's try to solve this. So first what we have to do, we have to take f dash of x, which is equals to 8x cube minus 27. Right. And for finding the point of local maxima minima, we have to equate this quantity equal to 0. Right. So that means f dash of x is equals to 0. Will implies 8x cube minus 27 is equals to 0, which is nothing but x cube is equals to 27 by 8. Right. And this is nothing but 3 cube by 2 cube. So if you take here cube root, then you will get x is nothing but 3 by 2. So this is one point we get by solving this equation. And if you put in the C, this is nothing but like a parabola kind of thing. So this will be a point of local maximum. Although we cannot conclude just by seeing this quantities. But here you get that this at x is equals to x is equals to 3 by 2. We can get either local maxima or minimum, right? Either local maxima or minimum. But still, we cannot say specifically that it is a point of local maxima. For that, we need much more higher derivative test for this. Okay. So now let's go to the next topics, which is mean value theorem. Is there any doubt over this particular concept, local maxima, minima? No? Okay. Now let's go to the mean value theorem. But before that, we will see one theorem that will help us to prove mean value theorem. That's Rolle's theorem. Okay. Before that, let's see a small remark. So this remark says that if we have a continuous function over some interval, and I think you guys are familiar that this a comma b, this is a notation for closed interval, right? Closed interval. And this open a comma b, this is a notation for open interval. And what is closed interval? Closed interval is nothing but a set of all x belongs to real number which are lying between a and b, including a and b, right? So that means a is less than or equal to x is less than or equal to b. And what is open interval? Open interval is nothing but all x belongs to real number in such a way that it is those x which are lying between a and b, but we exclude a and b here. That means we are excluding the end point of the intervals. Okay, so this is known to be the open interval. Open interval and closed interval. So what does this remark say? So remark says that if we have a continuous function over a closed interval, then the image of that continuous function is again an interval, right? So this remark says that if f is a function on closed interval a comma b, then the range and also the f should be continuous. Okay, so suppose f is a continuous function, not any function, continuous function. So if f is a continuous function on closed interval ab, then the range of this function, range of function means the values this function will attain over this particular interval, right? So that means f of closed interval ab you can say, or you can say range of f. Okay, so range of f is nothing but an interval itself. An interval, and the endpoints of those interval is nothing but the maximum and minimum value function will attain over this particular interval, closed interval. Okay, so it's nothing but again an interval with two endpoints. Okay, and what are those endpoints? So those endpoints are the minimum value of function and the maximum value of function over this particular interval. That means minimum of f of x, where x belongs to closed interval ab, and the maximum of f of x when our x belongs to closed interval ab. Okay, so this is a very nice property of any continuous function. So if you have a continuous function over some closed interval, then the range of that particular continuous function is nothing but again an interval with the endpoints are nothing but the maximum and minimum value of function. Okay, is it clear? Any doubt in this particular remark? Because it's very important thing that the range of a function with the domain to be interval is nothing but again an interval itself. With these two particular endpoints, we also know the endpoints of interval. Okay. Now let's go to the mean value theorem. So what does mean value theorem or Rolle's theorem or the Taylor's theorem works for? Right. So that means what is the motivation behind all these theorems? So suppose if you have a function, so suppose you know some properties of function, that suppose a function is continuous in closed interval ab and differentiable in open interval ab. So continuous in closed interval ab means it should be continuous at every point of the interval. Okay, and differentiable means it should be differentiable at every point of that particular interval. That means continuous over the whole interval and differentiability over the whole interval. So suppose we know that our function is continuous and differentiable over this particular interval a and b, and we know the other, the other values of function except this particular interval ab. So suppose we have some kind of this kind of scenario. Okay. So suppose we know that value of function over ab, and but we don't know what is the behavior function can occur over this particular gap. Okay, so this thing we don't. So what does all this theorem, Rolle's theorem, mean value theorem, and all those things? They actually give us a little. They actually help us to approximate our function using using derivatives over this particular short interval. Okay, so that's the main purpose of Taylor's theorem. Okay, so this is the main purpose of Taylor's theorem or any approximation theorem. That what we want to do, we want to use the differentiability of function to approximate the values of function at this particular short interval. Okay, so now let's start with the Rolle's theorem. So what is the Rolle's theorem says to us? So before going for all this theorem, one thing I want to say, you always have to keep in mind that your function should be continuous over closed interval AB and differentiable over open interval AB. And then only after these two conditions satisfies, then only you can apply any theorem. Okay. So this thing you have to first check. But see, if someone asks you the question about Taylor's theorem or Rolle's theorem, they already assume that it is a continuous. Not assume, they will give you very simple example which is visible that it is continuous over this particular short interval or open interval. Okay, so it's not always you have to verify, but you have to keep in mind that for applying all these theorems we need these two properties, continuity and differentiability over interval. Okay, so what is the Rolle's theorem? So Rolle's theorem says, so again we have two conditions. So if a function is continuous on closed interval AB and differentiable on open interval AB. And here we have three conditions: continuity, differentiability, and f of a is equals to f of b. That means function attaining same value over these two endpoints. Okay, so then the conclusion is f dash at c is equals to 0 for some c belongs to open interval AB. So that means you will get one c belong to open interval AB in such a way that the derivative is equals to 0 at that particular c. Okay, so let's try to understand this by graphically. What does this actually Rolle's theorem says? So Rolle's theorem says if you have a continuous function, then over this particular interval, and f of a is equals to f of b is given to you. So this function something look like this, right? Because f of a is equals to f of b. This is a, this is b. That's why I'm taking these 2 points to be here. Now, since it is continuous or differentiable function, either it can have a constant thing here, or it can go like a bump here or a cave type of behavior here, right? So one of them is possible. So if you have a curve like this type of curve, then what happens? You will find one point where your tangent is parallel to the x-axis. So that means at this particular c, f dash of c is equals to 0. So this is the graphical meaning that if you have f of a is equals to f of b and a function is continuous and differentiable over this interval, then you will always find a c for which f dash of c is equals to 0. Okay. Now here, what is the another scenario can happen? So another scenario means you can have more than one c. So suppose this is your a, this is your b. So over these things, you can have more than one c. More than one c means you can have more than one points where your derivative can be equal to 0. Right. So here what is happening? There are several points where our derivative is becoming 0. Right. So but Rolle's theorem guarantees us about one, that there always exists at least one c. Okay. So this is the Rolle's theorem. Now let's see the proof of the theorem. Is there any doubt over this particular theorem? Anything you don't you want to repeat or not able to understand? something. Okay, so let's go. Let's move on. Let's see the proof of this particular theorem. Okay. So proof. Again, we use the differentiability for the proof, obviously, and the remark which I told earlier, that this particular that the range will be the interval and the function is different. Okay. So first thing is the range will be an interval. So that means the range of f is nothing but a closed interval where the minimum is here, minimum of f of x, and maximum will be here, maximum of x. Now, suppose now obviously since we have a differentiable function and this minimum and maximum value obviously occur, so there will be at least one local maxima or local minimum point, right? So that means this will implies that there is a local maxima and minima, right? Now it can now there will always a maxima or minima point because our range of a function look like this: minimum of f of x and maximum of f of x, because of the continuity, right? This result came from continuity, and now we will use the differentiability. So since local maxima and local minima present, so this will implies there is a point. Is a point C in open enclosed interval AB in such a way that f dash at C is equals to 0. Right? But in the theorem, what we see, we say that C belongs to open interval AB. So what happened here? So if the C is equals to A or C is equals to B, then what does it say? So it says that f of A is equals to f of B is the local maxima and minima also. So what does it mean? So it means that our range of function is nothing but this closed interval f of A, comma f of B. But these two quantities are same, right? F of A is equals to f of B. But f of A is equals to f of B. So what does it say? So it says that our range of a function is nothing but a single point f of A or f of B. So that means it is a constant function. It is a constant function. Right. So if C is equals to A or B, then f will be a constant function. And if f is not a constant function, then C belongs to open interval AB. Right. So thus, if f is not constant, then this will implies that f dash at C is equals to 0 and C is a part of open interval A comma B. Okay. So this is a proof of Rolle's theorem. It simply used two facts. First is continuity of function. Because of the continuity, we have range to be a closed interval, and with the not simply a closed interval, but a closed interval with the endpoints to be local maxima or minima. And the second thing is differentiability. We know that our function is differentiable all over the interval, so that's why there should exist one C for which f dash at C is equals to 0. And again, we say that if C is equals to A or B, then our function is nothing but a constant function. Or else otherwise, f dash at C is equals to 0 for all open interval A. Okay. So this is the Rolle's theorem, and this is the proof. Is any doubt for this particular concept? Because it's a very basic theorem. We use Rolle's theorem to prove mean value theorem, and we use Rolle's theorem to prove Taylor's theorem also. But this is the one starting point, you can say. Any doubt so far? Okay, so let's move forward, because it's not that tough, but so for starting, it's important to understand. Again, one remark I want to say that Rolle's theorem guarantee it gives us a one C. That means says that there exists a C. It does not say that it always be a one C or you'll get one C, two C, or it says that there exists at least one point. It will give us an existence. It does not say that there are always a unique C, right? So this remark you can say that Rolle's theorem gives us an existence of a point C belongs to open interval AB such a way that derivative is 0. F dash at C is equals to 0. Not the uniqueness of C. Okay. So it means that we always get one C, but it is not the case that only one C, right? It can happen that we can have more than one C. For example, this picture you can always keep in mind. Right. So here there are so many points where derivative of function is 0 in between interval a comma. So this is an example. Fine. Now let's go to our next theorem, which is our mean value theorem. So what does mean value theorem says? Again, mean value theorem uses two conditions. Function should be continuous over closed interval AB, differentiable over open interval AB, and then we have some conclusion. Okay. So if a function is continuous on closed interval AB and differentiable on open interval AB, then there is a point. Again, this also tells us about the existence of a point. It does not tell us that you will get 1 point or 2 point or 3 point. It says that you will get at least 1 point. Okay, so that means that is at least 1 point. Okay, so if a function is continuous over closed interval AB, differentiable over open interval AB, then there is a point C belongs to open interval AB in such a way that the derivative f dash at C is nothing but equal to f of B minus f of A by B minus A. Right? So this is the main mean value theorem. So I'll repeat again, what does mean value theorem say? So mean value theorem says that if a function is continuous or closed interval AB, differentiable over open interval AB, then there is a C belongs to open interval AB in such a way that derivative of function at this point C is nothing but f of B minus f of A by B minus A. Okay, now let's understand what does this theorem says graphically. Okay, so this is our conclusion. So let's understand like graph. So it simply says that if you have a function, then it some sort of look like this. Okay, so then what it says? So it says that suppose this is a point x is equals to A, it is a point x is equals to B. That means the coordinate of this point is B comma f of B, and here we have A comma f of A. Then this theorem says that you will get one. You'll get 1 point where the slope of tangent is same as the secant line, the slope of this particular line. So what does I mean by that? So if you draw one line here, so if you draw the secant line, this line is known to be a secant line. So line passing through these 2 points, then whatever slope this line will have, you will get 1 point. Over that point, if you draw a tangent, then the slope of that particular tangent will be same as this particular. That's the graphical meaning of mean value theorem. So that means the slope of line capital L is same as the slope of tangent at point C. Suppose this is your point C comma f of C. Okay, so this is the graphical meaning of mean value theorem. Mean value theorem says that if you have a continuous differential function over some interval, then you will get 1 point where if you draw a tangent, then that particular tangent will be, you can say, parallel to that particular secant line. Secant line means a line which is passing through these 2 points A comma f of A and B comma f of B. That's the graphical meaning of mean value theorem. Is there any doubt over this particular concept? Any comment you want to make? Anything which is not clear? No? Okay. So this is the graphical significance of mean value theorem. Now let's try to prove it. So we use Rolle's theorem to prove mean value theorem. So what we do, we consider a particular function and then apply Rolle's theorem over that function. So what is this function? So let us say that g of x is a function is given by f of x minus of, here I'll consider one quotient f of b minus f of a by b minus a of x. Okay. Now since we have f is continuous in closed interval ab and differentiable over open interval ab, so it simply says that g is also continuous because g is nothing but combination of f and a linear function, right? This is nothing but a constant one. So g is continuous in closed interval ab as well as differentiable over open interval ab. Right. And here what is happening? If you calculate g of a, so g of a is nothing but f of a minus f of b minus f of a by b minus a of a. Right. And if we solve it, what we get? We get b f of a minus a f of a minus a f of b and minus minus plus of a f of a. Okay. So a f of a will get cancelled out upon b minus a we have. So this is nothing but f of a f of b. That means b f of a minus a f of b upon b minus a. And if you calculate g of b, you will get the same. So if we calculate g of b, so g of b is nothing but f of b minus bracket of f of a minus f of b, sorry, f of b minus f of a by b minus a of b. The simple calculation you have to do. So this is same as b f of b minus a f of b minus b f of b and plus b f of a by b minus a. Right, again b f of b and b f of b will get cancelled out. We will get b f of a minus a f of b by b minus a, which is same as g of a. Right, this is our g of a. G of a is same as 0. So this one implies g of a is same as 0. So what does it say? It says that g actually satisfy all the condition related which is required for Rolle's theorem. So that means we can apply Rolle's theorem over this function g. So that this can imply that by Rolle's theorem, there is C belongs to open interval AB in such a way that g dash of C is equals to 0. Right. So now what is g dash? So g of x is given by f of x minus of this particular quotient of x. So if we compute g dash of x, it's simply f dash of x minus this particular quotient, because x, if you take derivative, it will become 1. Okay. So that means g dash of x is equals to 0 will imply that f dash of x minus this particular quotient equal to 0. So it simply says that f dash of x is equals to f of b minus f of a by b minus a. And that's our mean value. So here we prove our theorem. Okay. So this is a little bit calculative, you can say, but the main idea is we will construct a function g of x which actually satisfy the condition of Rolle's theorem, and by Rolle's theorem we get mean value. Is there any doubt over this proof or the statement of mean value theorem? No. Okay. Anything you want to say about these two theorems? Okay, so let's move. So these are the two important and starting theorem of calculus if you are learning calculus then. Now we are done with the mean value or Rolle's theorem. Now let's go to the monotonic property of function. So what is monotonic function? Monotonic function means either increasing or decreasing function. So let's first state what is mean by monotonic functions. Okay. So a function f is said to be monotonically increasing if monotonically increasing over a certain interval, increasing on an open interval AB. If you choose any two numbers between these two, this interval, that means if for any x1, x2, such a way that x1, x2 lying over this particular interval with the additional condition that x1 is less than or equal to x2. In such a way that a is less than or equal to x1, less than or equal to, not less than equal to here, but here. X1 less than or equal to x2, less than or equal to p, then we can imply that our function preserve this inequality. That means if x1 less than or equal to x2, then f of x1 is also less than or equal to f of x2. So it says that f of x1 is less than or equal to f of x2. So this inequality is preserved here, less than. So this is known to be monotonically increasing function. Now similarly, we can describe monotonically decreasing function. So what is monotonically decreasing function? So if you have two x1 and x2 in such a way that x1 is less than or equal to x2, then we can say that our function reverses this particular inequality. Okay, so this is same for monotonically decreasing function. So here the inequality changes. So it changes over the last one. So it means this is greater than or equal to this is less than. So this is known to be monotonically decreasing function. Okay. Now let's try to understand how we can use differentiability of function to say that it is monotonically increasing or decreasing. Okay, so this is known to be monotonic function theorem. So this theorem says, so suppose again we need differentiability. So if f is differentiable in open interval AB, then by using the sign of derivative, we can say that it is increasing or decreasing. So that means we have three statements. So first is that f dash of x is greater than or equal to 0 for all x. For all x belongs to a comma b. This is sign for. Okay, so if f dash of x is greater than or equal to 0 for all x belongs to open interval AB, then we can say that f is monotonically increasing function. And similarly, if we have f dash of x is equals to 0 for all x belongs to open interval AB, in interval open interval AB. Okay, and this will implies f is a constant function. In open interval AB, and the third condition is if we have negative sign. So if f dash of x is less than or equal to 0 for all x belongs to open interval AB, then this will implies f is decreasing in open interval AB. So these are the three statements. So it's simple that we are just observing the sign of derivative and concluding the monotonic behavior of our function. Right, greater than or equal to 0 means monotonically increasing. And again, for all x, not for any but one particular x. If it is equal to 0, that means it's a constant function. If it is less than or equal to 0, that means it's a decreasing function. Okay. Now let's try to see the proof of this particular theorem. So again, as we use Rolle's theorem to prove mean value theorem, we will use mean value theorem to prove this particular monotonic theorem. Okay. So let's consider first case. So let's say x1 is less than or equal to x2. Then since our function is differentiable over this particular interval AB, and our x1 is and x2 are aligned between A and B, so we can say that f is continuous over close interval x1 and x2, because being differentiable over open interval AB means it is continuous over open interval AB. And if it is continuous over open interval AB, it is obviously continuous over close interval x1 and x2, because x1 and x2 is strictly greater than A and strictly less than B. It is lying between this particular A and B. So that's why we can say that it is continuous over close interval x1 and x2. And also, since we have differentiability here, we can also imply differentiability here, that f is differentiable in close interval x1 and x2. So that means we have condition, we have what I say, we have our hypothesis condition for applying mean value theorem. So we can say that by mean value theorem, what we can say, there exists one x naught. There exists x naught belongs to in between x1 and x2 in such a way that this ratio, that f of x1 minus f of x2 upon x1 minus x2 is actually equal to f dash at x. Correct. And now if we take this term over our left hand side, f of x1 minus f of x2 is equals to f dash at x naught x1 minus x2. Right. Now here, if we consider our first statement, so by first statement, what does it say is that if f dash at x naught is greater than or equal to 0. So since f dash at x naught is greater than or equal to 0, and x1 minus x2, then obviously if x1 minus x, I think I have missed here, this is x2 minus x2. Because b minus a we have to take, right? So this is 2 minus 1, 2 minus 1, 2 minus 1, 2 minus 1. Okay. So since x1 is less than or equal to x2, this ratio, this subtraction is also greater than or equal to 0. And it simply implies that f of x2 minus f of x1 is also greater than or equal to 0. It says that f of x1 is less than or equal to f of x2. So that means what we conclude? We conclude that if x1 is less than or equal to x2, then it's simply implying f of x1 is less than or equal to x2, f of x2. Right? When we are taking f dash at x naught greater than or equal to 0. So it's it will prove our first statement. But if you take if the derivative of function is positive for all x in open interval a comma b, then function is increasing over this particular interval. Is there any doubt in this theorem or the proof of the theorem? Similarly, you can prove the other two statements. Okay. If you guys have any doubt, then you can stop me in between. Now let's go to the next theorem, which is L'Hospital rule. Okay. So what is L'Hospital rule? L'Hospital rule gives us a way to calculate the limit of the form 0 by 0 or infinity by infinity. And if we have the function to be differentiable over over the neighborhood of that particular point, right? So what does I mean by that? So if f and g are differentiable again, so this is our L'Hospital rule. So L'Hospital rule says that if f and g are differentiable in open interval AB, except at a point C, C belongs to open interval AB, and also suppose that g dash at x is not equals to 0 for all x belongs to open interval AB, again except as C, and limit x going to C, f dash at x upon g dash at x is some L. Then what happened? Then if f of c is equals to g of c is equals to 0, or f of c is equals to g of c is equals to plus minus infinity, then we can say that this limit, x going to c, f of x upon g of x, is same as limit x going to c, sorry, here it is limit x going to c f dash of x upon g dash of x, and that is equals to L. Okay, so when you apply L'Hospital rule, just remember these conditions. First thing is your function f and g should be differentiable in open interval AB except at this particular point C. It can be happen that the function is differentiable at that particular point also. And suppose g dash of x is not equals to 0 for all x belongs to open interval AB, again except as C, and limit x going to C, this should be equal to sum. Then what happened? This limit x going to C f of x upon g of x, this is same as limit x going to C f dash of x upon g dash of x. So ultimately what we are doing, we are trying to simplify the limit, the expression given for calculating the limit using the derivative. Because we know that if we have n degree polynomial, then derivative will be n minus 1 degree polynomial. We can reduce our expression using differentiability. Right. Now let's try to solve one question here. So compute the limit x going to 1. This is x square minus 1 upon x square minus 5x plus 4. Again, I'll give you 2 minutes to solve this, and then we'll discuss. Try to solve it and answer in the chat box. Yeah, so it's a simple question. Let's try to solve it. So here what happened, these two functions you can consider f of x and g of x. So f of x is nothing but x square minus 1, and g of x is nothing but x square minus 5x plus 4, right? And these two functions are obviously continuous and differentiable over some small neighborhood of x is equals to 1, because again they are nothing but a polynomials, and we know that polynomial are differentiable everywhere. So we have all those conditions. Moreover, we have 0 by 0 form. That means if you calculate f of 1, so f of 1 is nothing but 1 minus 1, which is equal to 0. And g of 1 is 1 minus 5 plus 4, which is again 0. So here we have 0 by 0 form. And here you can easily observe that since g of x is equals to x square minus 5x plus 4, g of x is not equals to 0 for a small neighborhood around x is equals to 1. Because again, it's a quadratic function, we can break it down into two factors. One factor will be, I guess, x minus 1, right? And the another factor will be x minus 4, right? So this g of x equals to 0 only when x is equals to 4. So this f of x and g of x actually satisfying all the hypothesis for applying L'Hospital rule. So here we can easily apply L'Hospital rule and compute the limit. So the limit x going to 1 f of x upon g of x, this is same as limit x going to 1 f dash of x upon g dash of x, and f dash of x is nothing but 2x, and here it will become 2x minus 5, right? So now if we put 1, again it's a linear function, and this is a form of rational function, right? And we know that the limit of rational function exists if the numerator is not equal to 0 at that particular limit. So here at x is equals to 1, this quantity is not equal to 0, right? So you can just substitute x is equals to 1 and that will be our limit. So it is equal to 2 times 1 upon 2 times 1 minus 5. Okay. So it's simply 2 upon 2 minus 5, that is minus 2 by 3. You guys are right. So that's our answer. Okay. Is that clear so far? Now let's go to our next theorem, which is the inverse function and derivative of a inverse function. So first we'll try to understand what is the inverse of a particular function. So when a function have inverse, so if you have a function which is 1, 1 and on 2, that means injective and surjective, then that function is a bijective function and it will possess a inverse. This is the one definition. The another thing is if you can find a particular inverse function for that function. What does this mean? So it's a definition. So suppose f is a function from a set A to B, right? And then f is said to be invertible if there is a function in G from B to A in such a way that if we find out the composite function G composite f of x, which is same as G of f of x, this should be equal to x for all x belongs to. Now here we are applying f first. So for all x belongs to A, and f composite G of x, which is equals to f of G of x, should be equal to x for all x belongs to B. And if these two conditions hold simultaneously, then we say, and this one implies that f is invertible, and G is the inverse, and G is the inverse of f. And this G is actually denoted by f inverse, right? Okay. And G is denoted by f and then inverse here minus 1. Okay, so this is the notation for denoting inverse function, and this is a particular definition. That means we are finding explicitly inverse function. Right? G is that function which is a function from B to A. That means the codomain. That means the range of f to the domain of f, and holds these two inequalities. That means if you compose G composite f or f composite G, you will again get the identity function. Identity function means x. Okay, so this is the particular definition of inverse. So this definition you can also relate with our real number, right? So we say that the inverse of 3 is 1 by 3, because if you multiply these two numbers, you will get 1. 1 is the identity. So some kind of same thing here happening for functions also. Okay. Is there any doubt in inverse definition of inverse of a function? Yeah, now I'll cover the other part of inverse of a function. That means if a function is 1, 1 or on 2, then also we say that that function is invertible and we can find out the inverse of function. Okay, so that's another description of inverse of a function, or they also known to be a bijective function. So I think bijective is much more familiar than the inverse function. Okay. So I'll just define what are the bijective function, but before that, what is the 1, 1 function? Let's recall. I think you guys are familiar with 1, 1 function. So we say, so suppose f is a function from A to B. So suppose f is a function from A to B, then f is said to be 1, 1. Then f is said to be 1, 1. If for different input, we have different output. That means if for x1 not equals to x2, this is implying f of x1 not equals to f of x2. 1, 1 corresponding should be there, right? That means if we take different input, we are getting different output. That's the description for 1, 1 function. Now another type of function is onto function. So what is onto function? So onto function means when the range of a function is same as the codon. Okay, so suppose f is a function from A to B, and for every B, for every B belongs to B, there exists in A belongs to A in such a way that f of A is equals to B. So that means every element in the codomain have a pre-image, right? Pre-image concept. I think you guys are okay with that. So is there any doubt over these two definitions? One function simply says that if we take different input, we will get different output. And onto function says that for every point, we must have a one pre-image, right? Pre-image means for every B, we should be able to find one A in A in such a way that f of A is equals to B. Okay. So I'll ask you very simple questions here. Let's try to answer them. And then I'll tell you the ways to, there are 2 to 3 ways to say that a function is 1, or I'll let you know the graphical approach that if you have a graph of a function, then how can you judge the 1 or onto functions. Okay, so let's first try to solve some very simple examples. I'll give you 4 correspondence. Try to judge these are 1 function or not, or and these are A and B sets. So 1, 2, 3, 4, 5 is there. Again, these are A and B sets. 1, 2, 3, 4. A, B, C, D. Okay, so 1, 2, 3, 4. A, B, C, D. And suppose I have this correspondence. You have to tell which function is a 1 function and which function is not a 1 function. And same goes for onto functions also. Okay, so let's start with A. Is this a 1 function? True, false, and onto also. Not looking at the chat box although, but yeah. So this is the A1 is not a 1 function. This A1, this is not a 1 function, correct? Why it is not a 1 function? Anyone? Why it is not a 1 function? Correct, it is not a 1 function. Not 1. But why it is not a 1 function? It's very easy, right? See, two distinct input is actually mapping to a same output. That means f of 2 and f of 3 are same as B, but 2 and 3 are not same. So that's why it's not a 1 function. What about onto function? Is it onto function? Onto or surjective function? Is it a onto function? Yes, correct. Because there is for every element we have a pre-image. That means this element A has a pre-image 1. This element B has actually 2 pre-images, A 2 and 3. The C also has a pre-image 4. This D also has a pre-image 5. So that means yes, it is a onto function. Now let's come to B. Is it a 1 function? Yes, it is a 1 function, correct? Because every different input is going to different output. So yes, it is a 1 function. Now what about onto function? Is it a onto function? So yeah, it is a onto function because for every pre-image we have a for every element of a codomain we have a pre-image, right? So that's why it's also onto function. Now let's come to here. Now is it a 1 function? Is it a 1 function? No, correct. It is not a 1 function because two different input is mapping over same output A. So that's why it's not a 1 function. Now is it a onto function? Can you answer for onto? Is it a onto function? No, it is not a onto function because this D does not have any pre-image, right? So that's why it's not an onto function. Now let's go to D. Now, what can you say about this? Is it 1, 1 and onto? At least you guys can write yes or no. Yeah, it's a both 1, 1 and onto. Correct. So we simply says by this correspondence, the first one is not 1, 1, but it is onto. The second one is, so it is not 1, 1, but it is onto. The third one is also 1, 1 and onto. The fourth one is neither 1, 1 nor onto. Neither 1, 1 nor onto. And the fourth one is both 1, 1 and onto. Okay. So when a function is both 1, 1 and onto, that particular function is known to be a bijective function. Okay. So this is the definition for bijective function. So if a function is both, so if a function is both 1, 1 and onto, it is a bijective function. And every bijective function possesses an inverse, right? And bijective functions are invertible. Okay, so bijective functions are invertible. So that means if you have a bijective function, you can definitely find one function which is nothing but an inverse of that particular function. Okay, is there any doubt over the concept of inverse function? The first definition and the second correspondence of onto or 1, 1 and onto. Okay, so if you have any doubt, you can just tell me. Okay. Or else we can move. Now, let us see via some graphs that if we have some graphs, then can we say that those functions are 1, 1 or onto or something else? Okay, so let's first try for let's see one simple graph. So suppose I give you this parabola. Suppose this is some parabola with some vertex. So let's name it to be 1, x is equals to. So now, what can you say just by observing the graph? Is it 1, 1? Is it 1, 1? By observing the graph or by considering the definition of 1, 1, can you judge that this function is a 1, 1 function or not? Are you sure it is a 1, 1 function? What does 1, 1 function says? For different input, we should have different output. So that means if you find one point where the outputs are same, then it's not a 1, 1 function. Right? So again, I'll repeat, is it a 1, 1 function? Let's say something, at least yes, no, whatever you have in mind, just type. I get one answer, two answers. There are 14 people, right? So at least I should get 5 answers. Just give me a one guess at least. Is it a 1, 1 function or not? Okay. So many answers are no. Yes, you guys are correct. It's not a 1, 1 function. Why it is not a 1, 1 function? Because if you draw one horizontal line here, then this horizontal line is actually cutting our graph over 2 points, right? So that means if you find the coordinate of this point, then those coordinate are some point here. Let's name it to be x1, and some point here. Let's name it to be x1, x2. Then here x1 comma f of x1, and here x2 comma f of x2. But since it's a horizontal line, f of x1 is same as f of x2. So here, this horizontal line, what does it says? It says that x1 not equals to x2, but f of x1 is equals to f of x2. So, and this is not the definition of 1, 1. So it is not a 1, 1 function. This is also known to be a horizontal line test, if you guys remember. So let's see, horizontal line test. Now, what can you say about onto? Is it onto? So answer is no. It is not a 1, 1 function. So if you have a graph and you want to judge if it's 1, 1 or not, you just draw several horizontal lines. And if one of them intersect your graph at more than once, then it's not a 1, 1 function. That's known to be the horizontal line test. Okay, so that means you have to draw several horizontal lines, so many horizontal lines. And if one of them intersect your graph more than 1 point, then your graph is not 1, 1 function. Now, can you say for onto-ness, is it an onto function or not? For onto, can you guess using the graph? What does onto say? And I am assuming that it is a function from real number to real number. At domain and codomain are real numbers. So here I am assuming that f is from real number to real number. Okay. So what about onto? Are you sure it is a onto function? Because onto means for every point in codomain, we should have one pre. So that means there should exist one element in your domain for which function takes that element and map to that particular requirement. That's the meaning of onto-ness. If you have a graph given by this function, is it an onto function? Okay. Get one answer. What about others? You guys don't know false, please. Okay. Fine. So many answers are given. Yes. Okay. Okay, so I think you guys missed the point. So what does onto function says? Onto function says for every point you should get a pre-image, right? But here I'm saying that the function is from real number to real number. That means codomain is the whole real number, whole y-axis. So here if I consider this point, so suppose this is some y is equals to minus 10. Then for y is equals to minus 10, I don't have any pre-image, right? Because the function is not intersecting this particular line, y is equals to minus 10. So that means that is since y is equals to minus 10 does not have any pre-image, does not have any pre-image, it is not a 1, 1 function. Sorry, not a onto function. Not an onto function. Right? Onto function means for every element we need pre-image. But here this y is equals to minus 10 for so many points. You take any point over this negative axis. This does not have any pre-image. So it's not a onto function. Is that clear? Do you guys have any doubt? Okay. So if a graph is given to you and you want to judge the onto-ness, just simply think that it should approach to infinity from this direction and should approach to minus infinity from this direction. Then only it will be an onto function. If it restrict towards something, then it's not an onto function. For example, if I take this kind of graph, then you can easily find a pre-image for every element. No matter what horizontal line you will draw here, it will, yeah, it's not a 1, 1 function, but it obviously an onto function. Because for every y, we are getting one pre-image. That pre-image will be some x naught f of y. Sorry, f of x naught, which is y. Okay, so that's how you judge the onto-ness by judging the graph of it. Okay. Now let's go toward the main thing which we want to discuss here, that what is the application of derivative for finding the derivative of an inverse function. Okay. Or before that, we can, let's go to the derivative of inverse function first, and then we try to solve some example. Okay. So this is known to be a theorem. So this theorem says that let f have inverse, f inverse, and let f of x naught is equals to y. Right. Now here if we assume if f is differentiable at x naught and f inverse is differentiable at y naught, then we can find out the derivative of f inverse using the derivative of f. And the formula for that is simply f inverse's derivative at y naught is nothing but 1 by f derivative at f inverse of y. Okay, that means we are using the derivative of f for finding the derivative of its inverse. Okay, so that this is the formula, and the prerequisite is simply the differentiability of both function, which I mean it's 99% of the case that they will give you the differential function only, and then after that only they will ask you the derivative at particular point for f inverse. Okay, so in many cases, in several cases, the differentiability is always be there, but you should remember that the function should be differentiable. Then only we can apply this particular theorem. Okay, so if we have an inverse function and the f of x naught is equals to y naught, this is one thing, and both functions are differentiable over these respective points, then the derivative of f inverse at the point y naught is equals to 1 upon the derivative of f at the point of f inverse of y naught. And this f inverse of y naught is nothing but x naught. So this formula is also written as 1 upon f dash at x naught. Yeah, you can think about like this only, and this is also true. Because if f of x naught is equals to y naught, then f inverse of y naught is same as x. Okay, so these are vice versa. Whatever direction you want to say, you can say. But the main thing is you have to understand that the derivative of inverse at y naught is the derivative of f at x naught and the reciprocal of derivative of f at x. Okay, this is also known to be the inverse function theorem, but for the time being, it's a theorem for you, and it will compute the derivative of f inverse using the derivative of f. Okay, is there any doubt in this particular theorem?
Yes, ma'am. You again repeat this one.
Yeah, sure. So what does this theorem says? This theorem gives us a way to calculate the derivative of inverse function using the derivative of particular function. So suppose you have a function. So this theorem says that suppose you have a function f which has inverse f inverse. With f inverse in such a way that both are differentiable. First thing is both are differentiable at their respective point. That means if I am considering f of x naught is equals to y naught, I'm saying that f is differentiable. F is differentiable at x naught, and f inverse is differentiable at y naught. Then we can calculate the inverse. We can calculate the derivative of inverse function using the derivative of f. That means f inverse's derivative at this particular point y naught is equal to 1 upon f derivative at point x naught. This is the theorem. And this x naught is nothing but f inverse of y. Because f and f inverse are reciprocal of each other or inverse of each other. So if f of x naught is equals to y naught, it's same as x naught is equals to f inverse of y. Okay, so this is known to be the inverse function. Is that fine? No? Okay, and we can prove this theorem using by just simple inequality and chain rule. Because let's try to see the proof. So since f is the inverse of f inverse is the inverse of function f, so we have f inverse composite with f of x is same as x, right? And if we differentiate both sides and use chain rule, we can get our result. So by differentiation, what we get? We get f inverse of derivative at f of x into f dash of x, because chain rule, right? First this derivative and then inner function's derivative. That's why f dash x is equals to. So this will imply f inverse's derivative at point f of x is equals to 1 upon f dash of x, right? So here if we have f of x naught is equals to y naught, then it will imply that f inverse's derivative at f of x naught is same as 1 upon f dash at x naught, right? That means it's the same as f inverse's derivative at y naught is equals to 1 upon f dash at x naught. Okay, so this is a little proof of this particular theorem. But the main formula you should remember is this, that f inverse's derivative at y naught is equals to f's derivative at x naught. Okay, and not any x naught. This x naught is also specific to or related to y. Now let's try to solve some example over this. One example only I'll take. So here, first you will calculate the inverse and then try to find the derivative using this particular form. Okay. So suppose, so this is one question to you. Suppose f of x is equals to 3x plus 5 upon 2x minus 7. Then find f inverse's derivative at a point what we can take here. You can take any point. Let's calculate it. Okay. So this is your questions. I'll give you 5 minutes to solve it. Try to solve it and answer in the chat box. Okay. Try to solve it at least. At least make a guess. If you think you're not 100% sure, at least type a guess. You can type anything, type 1000 or something, but at least try to solve it. Okay. I'll give you 5 minutes. Let's see. Okay, so I have one answer. Let's try to solve this question. So here a function is given to us and inverse derivative 2 we want to find. Okay. So then what we can do? So first we try to find out a point x naught for which the 2 is the y naught, right? Because what is our formula? So our formula is that f inverse derivative at y naught is equals to 1 upon f dash at x naught. And what is the relation between y naught and x naught? That f of x naught is equals to y, right? Where f of x naught is equals to y. So first we try to find out one x naught for which this is the y naught is equals to 2. So that means, so now my aim is to find x naught in such a way that f of x naught is equals to 2. This is your first step. This is the first step you have to do when you have to apply some formula. We should know all the quantities over the right hand side, right? And the right hand side involve f dash at x. So I need to find x naught. Okay. So just substitute on the expression x naught. So we'll get 3x naught plus 5 upon 2x naught minus 7 is equals to 2. So what does it say? So it simply says that 3x naught plus 5 is equals to 4x naught minus 14. And if we do a little calculation, we'll get 4x naught minus 3x naught is equals to 14 plus 5. It's simply that x naught is equals to 14 plus 5, 90. Right? That means x naught is nothing but 90. So we get our x naught, right? So x naught is 90. Now we want to substitute in f dash at x. So first, now we will try to find out the derivative of this particular function. Okay. So the derivative will be, since f of x is equals to 3x plus 5 upon 2x minus 7. So now we try to find the derivative of this function. Now it's a rational function. So whenever we have a rational function, we apply the quotient rule for finding the derivative, right? So this will imply by quotient rule. What we get? We will get f dash at x is equals to the denominator square, that means 2x minus 7 square, denominator as it is, 2x minus 7, the differentiation of the numerator, and this is nothing but 3, correct? And then minus numerator, which is 3x plus 5, and the differentiation of denominator, which is 2x minus 7, so differentiation will become 2, okay? And now we solve this. So this is f dash of x is equals to, so this will become 6x minus 21 minus of again 6x. Okay, so this is, yeah, correct. And minus plus of 10 upon 2x minus 7 the whole square. So this f dash of x will equal to, now this 6x and 6x will get cancelled out. Minus 21 plus 10 will become minus of 11. So it will be minus of 11 upon 2x minus 7 the whole square. Now we want to calculate f dash at 19th. So f dash at 19th is equals to minus of 11 upon 2 into 19th minus 7 the whole square, which is equals to minus of 11 upon 38 minus 7, correct? 38 minus 7 the whole square. So it will become minus 11 upon 31st the whole square, whatever this is. Okay. So our final answer will be that f inverse derivative at 2 is equals to 1 upon f derivative at 19, and this is equal to 31st square upon minus of 3. Okay, so I have no idea that it comes like this complicated, but that's the case. Is there anyone who reached to the answer here? Way off, yeah, that's way off, but fine. Yes, Shaurya, do you have anything? Shaurya Singh, you want to say something? You guys can unmute yourself, right? I don't have any restriction over that. I haven't put any restriction. Okay. So is there any doubt in inverse function theorem or derivative? Actually, I have no idea that it will come this complicated, but yeah, the method you should know. At first, you have to find, this is your first step, finding x naught. The second step will be derivative of f, and the third step will be the substitute the values. This is your first step. Aim to find an x naught in such a way that f of x naught is equal to 2. If you complete this step, then you just have to compute the derivative and this substitute in the form. Okay. And then we find the derivative. This is your second thing. And then substitute it in form. Okay. Right. So now I'll conclude this lecture by giving the motivation for Taylor's theorem. Okay, and then in the next lecture we start from Taylor's theorem, and I'll cover all your doubts regarding activity and practices. Okay, so now let's start. Let's try to give us the introduction of Taylor's theorem. So far we learn about some approximations, right? Linear approximation, quadratic approximation. So what does those approximation do? So it simply says that if you have a function over a certain point with up to certain points, so suppose this is your point A, and the coordinates are a comma f of A, and you know the differentiability or you know the differentiability or continuity at this particular point x is equals to A. Then using the differentiability, we can give us certain approximations, right? So what does that mean? So by differentiability, by using the differentiability at A, differentiability at x is equals to A, we have certain approximations. Right? And those are linear approximation or quadratic approximation, right? So first one will be linear. What is the linear approximation says? That L of x is equals to f of x plus f dash of, sorry, f of A, I guess, f dash of A x minus. This is your linear approximation. Similarly, quadratic approximation we have. That's also f of A plus f dash at A x minus A plus f double dash at A upon 2 factorial x minus A. Okay. Now these approximation just works as an approximation. It won't give us the final value, right? So they are just approximations, right? What does Taylor did? Taylor find out a very particular error for every approximation and say that the function is equal to that particular expression. For example, if I say the linear approximation Taylor's theorem, then it says that f of x equal to, it won't give us approximation, it says equal to. That means Taylor actually specifically computing the error for these approximations. It says f of x equal to f of A f dash of A x minus A plus here there will be one error term. He is adding some error term, and this error term is also given by the second derivative. That means f dash at x naught upon 2 factorial upon x minus A the whole square. Okay, so this is the particular error term, and here the error, the point error x naught is also has a very specific position. That position is over this A comma x or x comma A, whatever we have. Okay, A comma x. So what does Taylor did? Taylor some kind of refine our approach toward the approximation of function, right? Initially, we have approximations, linear approximations, quadratic approximation, which uses the differentiability of a function. But Taylor tried to find out the error. What is the error between the original function and these approximations? And thus, that particular error comes out to be a very nice form, the derivative, right? And this particular error also depend on a very small quantity, which is this point x naught, and that position of that point is also specifically known to us. Okay, so that's the work Taylor did, and that's why the Taylor's theorem is important. because it gives us a very precise approximation of our function regardless of linear and quadratic. We have nth approximation too. I mean, if our function is n time differentiable and n time differentiable, then we can give us a particular formula or particular Taylor series for that particular. Okay. So that's the motivation behind Taylor's theorem, that Taylor some kind of refine our approximation and also give us the bound for linear approximation, quadratic approximation, and all kind of approximation. That we can actually say that what will be the bound of these all approximation make. Okay, so that's the job of Taylor's theorem. So in the upcoming lecture, we will discuss this particular concept in detail. For that, I'll recommend you to watch the videos, and then we try to see some of your doubts. I mean, yeah, we surely solve all your doubts over activity and practice. Okay. Is there any doubt so far, whatever topic we covered today? I'll upload this notes in the calendar using a Google Drive link. You can access from there. Yeah. Any doubt over this function? We cover up to introduction to Taylor's function, and in the next session we will cover the whole Taylor's theorem and whatever activity and practice doubts you have. Anything you guys want to discuss, or any questions, any query, or any problem, any technical problem also if you are facing, then you can tell me. I'll just post it to the right person. Yeah.
Ma'am, can you go back to the inverse function derivative?
Yeah, sure. Solution. This one.
Yeah, can you go to the example that we did?
Did I make any mistake? Can
Okay. Shouldn't it be like 1 over f derivative 19?
Sorry, what?
Oh, okay, you did that. Okay. I didn't see this.
Okay.
Thanks a lot.
Okay, so good to see you guys. We'll meet in the tomorrow. Yeah, Sunday session. And this is today's Sunday, Tuesday session. If you guys have any doubt, then
Thank you, ma'am.
you can say. Yeah. Thank you guys. Bye.
Thank you. Bye.